Well, good morning, everyone. Welcome to our October Town Hall. I couldn't be more excited to wrap up our 2020 season here in October with our last Town Hall, and couldn't be more excited to welcome Jeff Hammond, who is going to be our moderator today. Jeff has just come on as our executive director, and we as the board couldn't be more excited about what Jeff brings to us. So with that, Jeff, I'm just going to let you take it.
Great. Thanks, Courtney. Yeah, this is my second week, so I still have a little bit to get my feet on the ground, but I'm excited to work with IGSHPA membership and other organizations to move geothermal technology to the front line as really the solution for beneficial electrification, decarbonization. So we could talk all day about that, but I won't bore you with those details. We have a lot of work to do with training courses, providing industry resources, bringing value to membership. So I'm counting on good feedback from members like you, and hopefully lots of volunteers, wink, wink, to bring us to that next level. So I'm excited about that. Before introducing the star of our show today, I would like to just remind everyone of a couple of things. Let me switch slides here. On renewals, first off, we still have, you can still renew right now with no CEU requirements. We're still trying to determine those, and we'll update everybody once we're able to put those back in place. So right now, if you renew, you don't have the CEU requirements. Next thing on the list here for updates is town halls. This is the last town hall of the year, so please send any recommendations you may have for future subjects. We've really had a lot of good information out of these town halls, like the one Terry is working on today. It just gives us so much information for the industry. If you would send your recommendations to info@igshpa.org, and we'll put those on a list and get those started for the next session of town halls. So I would appreciate that. And last but not least, certainly very exciting, is the IGSHPA conference. And you may have already seen something about this, but if you haven't, make sure you check it out. It's in Nashville this year. We're working with National Groundwater Association, and we're expecting big things. We already have a lot of good speakers lined up. We have a great keynote speaker, panel discussions. We're even working on a group session on regulations and standards. And we have booths both in the IGSHPA Pavilion and part of the NGWA show. So go to igshpa.org to sign up. You can also send us an email at info@igshpa.org if you have any questions. Ought to be a great show. Looking forward to reconnecting with everyone, and let us know if you have any questions on that. So before we introduce Terry, just to let you know, is from a conference standpoint, if you have any questions, use the chat feature. We'll be monitoring that, and at the end of Terry's presentation, we'll read those questions. Hopefully we'll get a chance to go through all of them. If not, we'll follow up with you just as quickly as we can. So without further ado, I'd like to introduce Terry Proffer. I've had the pleasure of knowing Terry for almost 3 decades now. He's been involved in the industry since 1992, after a career as a petroleum geologist starting in 1979, after graduating with a geology degree in 1978 from Sul Ross State University in Alpine, Texas. He's designed closed loop ground heat exchangers for small residential applications to facilities exceeding 350,000 square feet of conditioned space, including various commercial, institutional, and military projects. Terry's the manager for Major Geothermal in Wheat Ridge, Colorado, a firm specializing in the design of closed loop ground heat exchangers, thermal conductivity testing, installation quality assurance, functional testing, and GSHP system forensics. So with that, I'll turn it over to Terry for our feature presentation.
Thank you, Jeff. If everyone will bear with me here, I'm trying to figure out how to share screen. Let's see. Okay. And start. Okay, how am I doing, Jeff? Are we getting where we need to do?
Looks great, Terry.
Okay, so if I don't touch anything else other than to advance slides, we should be good. Well, I appreciate the introduction, and it's a pleasure and an honor to be here. When I heard that Jeff was going to come in as our new director for IGSHPA, I became very excited. I think with Jeff's experience, it's the right direction to go. And just as a side note, I remember the first IGSHPA training class I attended, and Jeff was still working with water furnace at that time. And I walked in thinking, I can figure this out pretty quick. Oh boy, did I have a lot to learn, and still learning as it goes. So, but Jeff's probably one of our best brains in the industry, and I'm glad to know him and appreciate having him as running the top slot at IGSHPA. So with that being said, this is going to be a short presentation. Well, hopefully not too short, but we'll fill out the time. I'm going to provide you some examples of some forensics of some poorly performing heat pump systems, and otherwise some of them are easy to resolve, almost funny, to others that are pretty catastrophic. So with that, we'll start moving forward. So just my disclaimer, some general terms that we're going to go that'll be referenced throughout the presentation, such as basis of design, contract administration, et cetera, but down towards the bottom is a very important term, wild ass guess. So we have some situations resulting from wild ass guesses. So I would just like to reiterate that in this industry, there should be no rule of thumbs.
Terry, sorry to interrupt you. If you could maybe switch your displays, I think we're seeing your presenter mode.
Oh, that's what I was afraid of. Let's see. How do we do that, Jeff?
You should have a display setting in your PowerPoint presentation for switch displays, or you can unshare your screen and reshare it and just pick your other screen.
Okay. Let's see.
I would just stop sharing and start over again.
That's what I'll try to do here if I can figure out how to do that.
Yeah, you should see a red button that says stop sharing.
Got it. There we go.
Try resharing with the other screen.
How about now?
Looks great. Thank you.
Sorry about that, guys. I am technology challenged. So now if I can go back on my previous slide, how do you do that? I got it. So on this slide, learning objectives, I just want to go through real quickly that I'm trying to share some experience here on how we figured things out, where we started, and how we went about starting collecting information to shortlist what the possible causes were, and then also to resolve these issues wherever we could. It's for most projects, the solution, there may be multiple solutions. They can range from very inexpensive to very expensive. It just depends on the situation. One of the things though I found is if you get stuck on a project and you're trying to figure out what needs to be done, don't be afraid to call in someone with the experience you need. I have a heck of a phone directory and I use it quite a bit. So one of the problems with a problematic ground source heat pump system is by the time a third party forensics person is called in, the client's got a pretty bad attitude towards the system. So we don't like train wrecks, and that's what the client is typically thinking of when no one on the original design and construction team can't figure out what's going on. So where do we start? Well, you got to listen from the client, what's his problems, the contractors, if the mechanical engineer, everyone that's involved. I can't tell you how many times I found key bits of information on like a bad performing school, just talking with the facilities guy that no one was paying attention to. And he's the one that came up with, some key information on a system that we were trying to resolve. So you want to listen to everyone, don't discount anyone. You want to look at the history, when did the problem start, review of original as-built documentation, etc. Maintenance history, identify, issues with changes in operation, controls, that sort of thing. I always try to get if it's a commercial project where a mechanical engineer was involved, or if it was a problematic home where a mechanical contractor did his own design and installation, I always try to go back to that person and ask them what their opinion is. It helps to get all eyes on the project. But one of the things you'll find is once you start collecting information, you'll see patterns emerge. So the other thing to consider is some people make assumptions that are incorrect. So you have to understand also that while information is helpful, someone might be making assumptions that could lead you down the wrong road. So you have to consider all these factors. So one of the things I've come up with for the following examples is my lemonade scale. Somewhat accurate and scientific. 1 to 5, 1 lemonade, fairly easy to correct, not a big deal, to worst, which can be catastrophic. So we don't like to see the high lemonade count on big projects because it hurts our industry, hurts the client and everyone involved with the project. So the first example is a residence, a very nice installation. Gentleman's actually a mechanical contractor in New Mexico. He took an IGSHPA course that I presented some years ago. Before he started practicing on his customers, he wanted to practice on himself. So he put in a system in his own home, both a radiant floor and a forced air system. So he had both water to air and water to water heat pumps. So he did everything by the book. He did a good manual J. We helped him out with a ground loop design. It was a slinky. It went in a little bit oversized, which is no problem. But he had one problem at startup. His water to water heat pump would continue to run until it would lock out on head. So we had several phone calls, ran through the troubleshooting checklist. All the variables looked good, but it was pretty obvious to me we had a controls issue. So I asked him what kind of aquastat he was using. So he was using a strap-on type. So he did put in a immersion well tank. So we put in the correct aquastat there, but it was still locking out. And unfortunately, I've run into this with a lot of newbies on radiant floor systems. And what he had done is he put in the aquastat, but he did not put in the thermal paste in the well. And once he did that, problem solved. So that was a fairly easy one. And that was his only problem during the entire installation. He did a very good job. So we'll give you another example. This one's a school. It was a new construction school in Wyoming. Of course, some parts of Wyoming can have very, very stout winters. A lot of the classrooms, however, the first winter would not maintain set point. A lot of discomfort. Everyone's, of course, blaming the ground source heat pump system because no one understood it. We couldn't get initial information from anyone. I was working with the mechanical engineer, the mechanical contractor. To put it as politely as possible, was of no help. So the design was blamed. We had a lot of people that made assumptions that were condemning the system, us, our ancestry, and everything else. And they had started this with all the problems without contacting the engineer of record who I was working for initially. So that's something also to keep in mind if you're involved with the system that has problems and you're the last to hear about it, you'll be the one thrown under the bus. So what we found after making a site visit was that the ground loop was actually working fine. They thought they were getting fed 20-degree water. They were not looking at the supply water temperature. We were actually in the well into the 30-degree range supplying the heat pumps, which was pretty good. The heat pumps were not locking out, but they were struggling. So we redid load calcs, et cetera, et cetera. What we found was, after site visit, that the perimeter envelope insulation was not to spec, and there were large gaps allowing outside air to come into the room. So in essence, the closed loop ground source heat pump system in some rooms was trying to heat the county, not just the space. So once that was corrected, the ground loop actually runs in the low 40-degree range most of the time in the middle of winter, and it works just fine. But we gave this one 2 lemonades because of the PIA factor, which is pain in the backside, and but we got it done. And one of the things we learned from that is we should have visited the school early on when all of this was becoming contentious. So that's just something that now when we have a problem on a system, or I hear of someone else having a problem and they want us to know what's going, or want us to help them out, after I review whatever documentation, I want to make a site visit as soon as I can. Case number 3, we had a retrofit on a historic registry school. It was here in Colorado, built in 1925. It did not have a consistent mechanical system. The school district had enough and said, hey, we want to put a ground source heat pump system in this, retrofit it. So it was done. Getting ready to start the fall semester, though, the heat pumps were locking out. And this was right, just within a few days before school was to start. So everyone was pretty excited. So the engineer of record was unable to make a site visit. So they asked me to go down, which I did. I went through a lot of questions on the startup, are the strainers clean? Are you getting water to the heat pumps, et cetera, et cetera. Project manager claimed all the check listed items were okay. However, he was making some assumptions. I got down there, it took me about 2 minutes to figure out the problem. On the hose kits, the ball valves were in the off position. So once we opened them up, guess what? All the heat pumps worked and everyone was happy. So that one was an easy fix. So example number 4, another school, about a 60,000 square foot new construction. Initially, after the school opened up, they were having heat pumps dropping offline. They were having a problem keeping up to condition. They just weren't working. So we found out that the water makeup device in the mechanical room was working at full capacity. This was before we made a site visit. So we saddled up and headed for the school. Well, while I'm walking up to the school, I see a landscape crew finishing up planting some trees, and they're using a big backloader to drive down key posts to support the trees. And all of a sudden we had a bit of an artesian issue, and I went over and I thought, man, this is right around where our header lines are at. Well, I could tell there was propylene glycol in the water. And I thought, I think I know what we have a problem here with. And sure enough, we started excavating. Well, it's kind of funny. We had lots of experts there helping us finding the leaking header line. But I have to hand it to the landscape crew with they hit a blind target dead center on our header pipelines. I don't know if you guys can see that key post. It's surrounded by all that bubbling water. Well, that's from puncturing the high density polyethylene header pair lines. So that one was pretty expensive to correct. The landscape company was not happy because it was their responsibility to avoid such things like this because there's plenty of as-built, et cetera, but of course we had to repurge it. There was a lot of dirt contamination in the loop, so it was a mess until it got corrected, but it had to be repurged as well. All right, our next example, it's actually the same school. So after the ground loop was repaired and repurged, after the first year, the utility bills were outrageously high. No one could figure out what was going on. So we go back out again. And just a little background, this was a decoupled loop, and this is important to understand on this project, that it was a very efficient design where the building loop was circulated without engaging the ground loop until the interior building loop needed to be warmed or cooled, and that's when the ground loop would come into play to temper the building loop. So our first clue was we had a lot of cold piping inside the building. This was winter when we were visiting. But on the ground loop supply, we were at 58 degrees. Well, that rang a bell. That was kind of our standard undisturbed temperature. Our ground heat exchanger return water temperature was also 58. Well, I got back into the mechanical room from the injection bridle and found that the pumps weren't working. The other clue was the controls contractor. These were water to air packaged heat pumps. They had backup strip heat. Well, he made the backup strip heat his first stage heat, not for the heat pump to work. So between that and not the injection pumps weren't working, no wonder they had high utility bills. So we got all that corrected, and guess what? Everything worked fine then. So we don't know why the controls contractor and the engineer miscued, but it's just another lesson that if you design something, you need to perform some contract administration to make sure that everything's the way it should be. So that was only a 2 eliminator, not too bad. And just to recap, that was our injection system. And once the ground loop injection pump system was activated and controlled correctly, we were good to go. Now, we had a fire station here in the Denver area, and fire stations, the living areas are really residential in operation, because the firemen are living in there, and they it's their home while they're on call. So system was working fine until late summer, and we had a heat wave, and the heat pumps wouldn't stay online. Our entering water temperature of the heat pumps was exceeding 120 degrees, and they didn't like that. So we didn't hear about it until after everyone was really mad. So, I got the blame initially, which is typical for the ground loop design guy. So we've looked over everything, looked at our loads and loop calculations and all that, and we thought we should be pretty good. It was a big slinky field. So what we found was they had value engineered out the energy recovery ventilator. So they just had this hole, literally a hole, feeding outside air into the building. So again, we're trying to cool the county instead of just the building. So we closed off the hole until an ERV could be installed like it should have been. And immediately the system started working, and actually within a day or two, we dropped the loop field down to about 85 degrees. So again, those of you that are experienced in the construction trades, beware of value engineering. Beware of cause and effect if you do these things. Have another school. This one is in downtown Denver, about 100,000 square feet. A good sized loop field, 48 holes by 500. But after a year or so, everything went sideways. Turned out the water was contaminated. One of the earlier investigators, who didn't really know anything about ground source heat pumps, had said, well, and he had checked the strainer. He said there's this thick brown slimy sludge in the system. Well, he was right on the money, because it was thick, brown, and slimy. And by the time I was called in, the original engineer of record had gone out of business. So guess who got the blame? I had explained to people, no, it's not bentonite grout. I took one whiff of the water and I knew it was biogenic. So I asked, did anyone tested the water for bacteria? They had not. I asked, when had any water tests been done? Well, it never. So anyways, it was found to have a lot of bugs. They were, of course, eating the propylene glycol because that's a type of a glucose. So they were going to town on that. So the system was flushed, cleaned out, and routine testing initiated, and the system's working fine, but they are monitoring their inhibitors on that. I did not put it in the presentation, but one of the things they were missing was a coupon rack, which should be on every commercial scale project, in my opinion, to ease testing. And no one read the O&M manuals, by the way, which is another common thing. So we had a side issue, though. They had some really high utility costs that they noticed. So I looked at all of their bills, and I noticed they had some really ugly demand charges. So it wasn't necessarily power consumption. Well, turns out once we got some trend data, that every morning about 6 a.m., they fired up all the heat pumps at one time, which also means all all the pumps fire up, et cetera, et cetera. So we got them to relax their night setback, allow the heat pumps to come on incrementally. In fact, I actually advocated to let everyone with their own thermostat just pick whatever they want and let the system coast, but they didn't want to do that. But we did get that resolved quite a bit, and that was a fairly easy correction once we understood what was going on. So we had another ground source heat pump system. It was new construction, pretty good size school. Found out all the heat pumps had sufficient capacity. The ground loop was sized correctly. In fact, it was fairly well done as far as, you know, having enough borehole capacity, but found out that some of the header pairs were having to be abandoned because no one could find the leaks and they were not holding pressure. So we found that the loop was oversized sufficiently that we could lose a lot and it would still work fine. We did realize though that the loop design, the header pairing was really strange. They had as many as over 30 holes on one header pair, and it took quite a bit to purge that out. Due to all the contamination, we spec'd and installed a filtration plant in the mechanical room, and it was collecting a lot of debris. So there was lots of bad causes on this one. There's both design and construction issues. There's bad headering. The loop installation crew was bundled. They had one guy drilling, another guy looping, another outfit from out of state coming in doing headering. No one was talking. It was pretty bad. No one understood purging. They thought they'd purge the loop field. They were way short. The reason they just got pure water back is because they were only getting flow through part of the loop field. So it was never enough to get it fully charged, as a matter of fact. So it actually went into litigation, and we were involved with that. But we are getting things resolved now. So this is just some pictures of the large purge pump system we put together, and that in the lower right corner that's the filtration plant that we installed in the mechanical room. So it was both the engineer and the installation contractor, they did not intentionally set out to have a problem, of course. They just didn't know what they needed to know. Had this system had some oversight with an experienced third party, none of this would have been a problem. As it turned out, we've had to put in a new loop field. In fact, the new loop field is going in as we speak because of the limited area that we have left to deal with. We're putting in 80 holes by 600-foot depth at this school because 90% of the field has failed now due to leaks, and all the trenching and whatnot to go in and check where to seal it up. It just was not cost effective. There was a lot of other issues involved. So that's a 5 lemonade project. Very expensive. So my next example number 9, is a residential installation. This was actually down in New Mexico, very high-end home. It's beautiful, but it never worked. The person who did the installation did his best. He just didn't know what he needed to know, and it was a lot of things were done by assumption. and both in the design and the execution of the installation. So the client, after we went through all the forensics on the design and did our own load calculations, we found multiple problems with the infrastructure, controls, everything else. So we had to figure everything out on site and start from scratch. The client asked me, what's the best way to go? And I said, well, honestly, unless you want to spend, another $40,000 or $50,000, you're probably money ahead to put in a conventional boiler, furnace, and air conditioning system. But this gentleman was, he really believed in ground source. He knew that he had a bad design and installation, and he wanted it done right. So we redesigned it, and it is now up and running, and it's fine. But that one was definitely a 5 lemonade project. Now for the last one, we've got an open loop system. And this is for a law enforcement facility down on the Gulf Coast of Texas. It is a bit of a mission critical facility. There's a central plant heat pump chiller servicing a VAV system, and it was fed by 3 source wells, and then the water was reinjected into the 3 reinjection wells. So before going down, we reviewed the loads, basis of design, et cetera, et cetera. We had all kinds of problems with the controls we found. What we found was the water was really bad. The 6-pipe chiller was not talking with the building BAS system, and no one had figured that out. We found all kinds of problems. So, for example, the chiller would show a fault and alarm, but it wouldn't communicate through the BAS system. The facility guys would literally take picture of the faults and alarm screen on the chiller and email it to everyone. That's the only way they could figure out how to communicate with this thing. The piping corrosion was so excessive. Any metallic pipe was on its way to failing. So we found that the water was not only very aggressive chemically, it was loaded with fine silt and sand. The water chemistry on the water wells was so bad, livestock couldn't drink it. What they had done, they tapped into a very shallow aquifer, unconfined groundwater that back in the day had been contaminated from local oil and gas production. Of course, the laws have caught up with that now, so that's not a problem anymore. When the intermediate heat exchanger was disassembled, and I knew it was a problem because even without putting a thermometer on the supply and return sides, you could tell there was no heat exchange going on. It was totally plugged, and they only had one heat exchanger. So when the one heat exchanger was pulled down to service and clean it, the whole building had to shut down. So that was remedied by putting in a lead and lag heat exchanger. So they wanted to stick with an open loop system. We brought in a local hydrogeologist, told him what we're looking for and what we needed. He said, well, we need to tap into a deeper confined aquifer where the water's better. So we did that, resolved controls, outside air, ventilation conflicts, et cetera, et cetera. The 3-leg chiller, when it's a 6-pipe system, and it was trying to scavenge heat rejection from cooling for those zones that needed heating when it was necessary. What we found was in one visit down there, actually all the building was in heating, and the system was not trying to access heat from the well water. So it was failing. So that had to be corrected. So lessons learned. The engineer did not understand that he should have engaged a hydrogeologist to design the well system. They'd gone out and just asked the local water well driller, said, hey, we need this much flow rate, give it to us. And the guy didn't understand what the water was going to be used for. What we also found in retrospect, had they gone with a closed ground loop, it would have been cheaper than the 6 supply and reinjection wells they put in, especially when you consider all the problems with the open loop system. So mechanical controls contractor were not on the same page. And again, some gray-haired peer review would have caught these issues and saved a lot of grief. So I've got a bonus here for you guys. This is a recent issue for a regional airport. It's actually in Gunnison, Colorado. The terminal was getting a ground source heat pump system. We were all proud to be involved with that. When we did our TC test, we thought we were going to have really easy drilling conditions. But as the driller started advancing in the boreholes, part of the field, he was having his equipment damaged. They were really having problems with fluid losses, etc. So we did a lot of offset holes to make up and get the thing done. Well, when we started headering, we found out what the problem was. When the headering started, the excavator ran into large blocks of concrete, reinforced concrete with rebar, a lot of scrap steel. What we were drilling into was the old Denver and Rio Grande Railroad station, where they had a turntable and switch yard. And no one realized that until we started talking with some of the older generation in the community and said, oh yeah, we could have told you you're right on the turntable there. So anyways, the driller did get a change order on that one. So to wrap this up, and by the way, I assume this presentation will be available to everyone as a PDF later, but I've got some comments at the back here that, for example, simple is better. I think we all know that are experienced in this industry. Peer review, if you're new to the industry, it pays to bring in some people that have been around for a while that know what they're doing or been there and done that. Full commissioning, which is peer review from concept through installation, especially on bigger projects, I'm a firm believer should be done, especially where you have design team that is doesn't have a lot of background on ground source heat pump design and execution. Should also, when designing a system, one should always be thinking, okay, what's it going to take to maintain this system? You know, just because it looks good on paper, can you really maintain it? We've seen a lot of overly complex systems put in rural applications, and that's a recipe for disaster. Control sequence of operation should always be as simple as possible. We have also found some folks putting in cheaper water source heat pumps on a closed loop system, and they wonder why they fail when the water gets too cool or too warm. So we keep an eye on that when we're hired for third-party review. Headering, having too many ground loop circuits on one header pair, you can't not only be difficult to purge the air out of it, you may not fill that loop filled up completely with water, so you're losing capacity if you don't have a full capacity ground loop. Reducing manifold design is very important. I find a lot of people do not understand how to do that, and it can really make a big difference on a bigger project. Excuse me. The other thing is, on our, when we produce our CAD drawings, we're very detailed. We just don't have a site plan. We will have a detail sheet that describes in detail the reducing manifold, how we want the penetrations in the mechanical room to be isolated and sealed, that sort of thing. So even to the mechanical room header, how that is to be configured, and how it should be isolated along with the correct purge ports. Some of the bigger problems we've seen is problems with controls on a ground source heat pump system, where a controls contractor will try and treat a ground source heat pump system as if it were being driven by a boiler and cooling tower. There are differences. It's amazing to me, PT ports or PEATS plugs should be on every mechanical device, whether it's heat pump or whatever. They're one of the fastest way to get a read on pressure and temperature, and to start solving things for maintenance and any other efforts you're looking at. We also rarely see, whether it's residential or commercial, we rarely see anyone doing a startup test on their heat pumps, which for most heat pump brands in their IOM manuals is clearly outlined, but no one ever does that. And that's important because it establishes a benchmark for later comparison for maintenance and service. Would like to see people be a little more cognizant of doing that. Just like to reiterate, simple is better. And ultimately, what you're trying to do with forensics work is to get the train back on the tracks. That's all I got. Hope you guys enjoyed it.
Thanks, Terry. Great presentation. I guess my main takeaway is we don't want to be on Terry's list of examples, right?
I'm nice about it, though.
All right, we have a lot of good questions and comments. So if you can stick around, Terry.
Absolutely.
I'll start reading those. First question is, what does lockout on high head mean?
Okay, so typically on a compressor within a heat pump, if you're not getting enough water flow or the temperature is not good, and you can't get rid of the heat on one side of the refrigerant circuit, that head pressure on the compressor is going to increase. That's typically on the cooling side. And what will happen is the unit is going to overamp and it's going to lock out on safety. So it's an indicator that you have a problem. And the other alternate to that is low suction, typically on the heating side, where your water temperature and flow rate on the source is too low, and the heat pump is struggling to suck heat from the heat exchanger, from the water to refrigerant heat exchanger, and that can also cause a lockout.
Great, thank you. Then we have some comments here. Looks like some people have run into similar problems on middle schools, having the geo lines hit, commissioning agents, some experience there, jumpers on heat pumps for antifreeze settings.
Oh yeah, that's a common one.
So there's a lot of good feedback here on people who have had some experiences similar on a police station that you mentioned. Here's another question, Terry. Is there a top 10 of issues that you commonly see on failed systems?
Yeah, I'd probably say controls are the biggest problem on light commercial and commercial scale projects. Rarely do I see a ground loop being undersized, but I have seen a lot of problems with the way ground loops are misheadered. That'd probably be number 2 on my short list of key problems, where you're not getting full capacity out of the ground loop because you got a bad manifold design.
Okay.
Oh, the other issue, it's related to controls, especially on schools and commercial buildings, is outside air mismanagement. But that's we see that quite a bit, where we had one project where, well, we've seen it on more than one occasions, where economizers are left wide open in the middle of summer and winter. And, you know, the groundlet is only designed for the loads of the building, not the county. So a little bit of stress on them.
For sure. So there are probably many others, but that's a great list.
Yeah.
Next question. Did the engineer of record allow the ERV to be value engineered on the one job where they just were missing it?
This was one of those jobs where the general contractor took it upon himself to pull it out. They were running over budget, and the engineer of record was not contacted. And on that project, when I was out there, that was one of the things I said, why haven't you called Dan? He said, well, he's just the engineer. And I said, well, he's the one responsible. Anyways, make a long story short, we got him out there and I showed him what I found. And he said, yep, we need to put that back in. So they did.
Very good. Next question. Do you find any accessories are more beneficial than others on manifolds or interior mechanical systems to help determine any issues? Example, thermometers, pressure gauges, pressure transducers, etc. And where do you suggest these accessories be installed?
Good question. What I would like to see on every, especially like commercial project, would be trending of supply and return temperature and flow rates, because you can do so much with that trend data for not only service and diagnostics. You can also later on figure out, oh, how good was our original design, that sort of thing. The problem I have with gauges, whether they're digital or analog, is they can get out of whack. And I'm for putting them in a mechanical room on the header pairs and whatnot. Excuse me. But I would also like the PT ports in there, because you can always use a handheld instrument that it has the same calibration for every time you put that unit in to measure temperature or pressure. So, but yeah, I'm all for gauges, but I'd really like to have more trend data. In fact, I believe ASHRAE has a team that is trying to solicit post-installation ground loop performance, and they're looking for trend data examples right now.
Great. Okay. What's your thought about how we can use and/or develop codes and standards to encourage successful GSHP installations or on much larger scale? Or maybe you think there's a better or different path in codes and standards. Maybe it should be standards and codes as the right order.
Well, as you know, Jeff, you're on the CSA. You are the CSA head honcho, and excuse me, there's a role for standards, but I think it goes back to get our industry moving forward, to take up more of the mechanical market share, is better design and installation. And that goes back to training, not just training residential and commercial contractors, but mechanical engineers. And that's why I'm hoping the new IGSHPA will step up its game on the training and recognize these deficiencies, because yeah, codes and standards are important, but that's just you know, a lot of code inspectors are not the guys that design these things. They're just looking to say, okay, is that up to code or standard or whatever? That doesn't mean you're going to have a good design and a good installation that's workable. That goes back to whoever's designing the system and installing it. So I think the big shortfall in our industry is competent training right now.
Yeah, great, Terry, thanks. And one of the things that we want to do or are going to do as IGSHPA is provide a lot more resources. You know, we have so many members with incredible experience and knowledge. why not take advantage of that information? So those are one of the things we're going to be talking about is, how do we make that more available? There's a session at the conference coming up that's really a working group, and we're going to start down that path. No point in not sharing. So thank you, Terry, on that one.
Absolutely.
So here's the next question. Have you ever seen a fault diagnostic software used successfully on a ground source system?
I'm sorry, I didn't hear that, Jeff.
Oh, sorry. Have you ever seen a fault diagnostic software used successfully on a ground source system?
It depends if you're talking about on the heat pumps or a building automation system, or
it doesn't really specify. Wonder if Matt is still.
Well, let's take it from the heat pump. A lot of heat pumps have self-diagnostics to a limited extent. And so the IOM manuals can be used to look at those fault codes and narrow down a cause. I will caution you, there are misinterpretations. We just had one recently where had a lot of heat pumps on a school dropping offline, and the facilities guy said the water temperature too cold because that was the fault code. It was low suction, and the unit was tripping out. And I get down there and I said, well, your other heat pumps are not locking out, and your supply water temperature is 45 degrees, which is fine for an extended range heat pump. That's manna from heaven. What it was, he had very low flow. The reason being his strainer was almost clogged. And as soon as he started cleaning out the strainers and the heat pumps that were locking out, so the low flow he was misinterpreting as low water temperature. So just be aware when you're going through like a heat pump fault code diagnostics regime to make sure you're interpreting what you're looking at correctly and not make assumptions. And on BAS systems, of course, those are custom. We've seen problematic systems where the ground loop temperature was supposedly being trended and was being mixed up with the entering and return water temperatures to the heat pumps themselves. So the controls guy just, he's doing the best he could, but he didn't know what he needed to know. So that goes back to, if you design the system, it's good to go out and talk with the people installing it, make sure everything's copacetic, and there should be a startup test to identify those issues too. Just my opinion.
Great, Terry. Well, it looks like we are about a minute from half past the hour. I certainly appreciate everybody's time. Terry, thank you very much for doing this presentation. We'll try to stay off your list. And, hopefully, if there's anything that comes up, if you have any topics, don't forget to send to info@IGSHPA.org for next town halls. Hope to see you in Nashville, and thanks again.
Appreciate it. Thank you, guys.